Science is built up of the facts, as a house is with the stones. But a collection of facts is no more a science than a heap of stones is a house. Henri Poincaré. What Noether theorem has done is it's connected an abstract principle of theory, it's a symmetry, to this practical benefit. And let me give you some specific example of the Noether's theorem. Because it really is a pretty deep mathematics and a little bit hard to visualize. Example number 1. I sit at this table and I start doing physics experiments. Okay, I knock the ball against one another, billiards balls, and I start tabulating laws of physics, Newton's law and the laws for the electricity and magnetism, and the laws for the strong force and weak force, just by doing experiments. Okay? I am not talking about the detail of the experiment. I'm talking about the laws of nature that I'm conducting from them. Now, I pack up my gear and I move next door, and I do the experiment again. People have done this, and the laws of physics next door are the same as the laws of physics here. Newton's laws are true in Australia, and Japan, and the United States. They are the exact same laws of nature, so this is a symmetry, okay? When you look at a physical system, the laws are unchanged when you view it from the different perspective. In this case, your perspective is looking at it from the different place. We call that a translation symmetry. We call that translation symmetry. Translation symmetry. Translation not having to do with the language, but just meaning translating yourself along some line. This is a symmetry of nature. And the Noether's theorem says, when you have a symmetry of nature, there must be an associated conservation law. Yes. Now what you can't do is to just guess what is going to be conserved. But Noether's theorem is really a mathematical theorem, and you can derive what is conserved. And when you do the math, and you discover that this particular symmetry, translational symmetry, leads to a conservation of momentum. When objects are moving along and you have a crash, if they started off with some motion of the light to my right, then in the end, the mess, the blob of stuff that's all crashed together will still be moving to the light, unless there is external force. But that's a complication to story. Conservation of the momentum, very useful, connected to the symmetry of the where you are looking at the laws of physics, very abstract. And now you can test the conservation of momentum in the laboratory, but you can also test for translational symmetry, and it's indirectly doing an experiment for you. So, for instance, how far can I go and still have the laws of physics be the same? It's an interesting question. Astronomers have looked at the galaxies far away, right? Galaxy is the nearest one. The Andromeda galaxy is the nearest one, but it's extraordinarily far away, millions of light years, and yet I'm going to argue that the law of physics in the Andromeda galaxy are apparently the same as the law of physics here. Now, how do I know that? There is no aliens who have told me the laws of physics there. But I can look at the star in the Andromeda galaxy, and it's not the same colors and the same light and the same temperature. Oh, I'm sorry, and it's got the same colors, the same light, and the same temperature, and the same distributions. All of the laws of physics and pretty much all laws of physics have to be put together to explain something as complicated as a star. Aha! The ultimate object is the same in the Andromeda galaxy as it is here. So this is a very powerful evidence that the laws of physics are the same all the way over there. the conservation of momentum seems to be an incredibly well-proven fact of the nature, and it's well-proven through this mathematics. It's kind of a wild concept. The connection between the position and momentum is definitely not obvious. I am not implying that you should understand Noether's theorem intuitively. Why momentum? And as I said, the answer comes out of the math. There is a hint from the quantum mechanics. The Heisenberg uncertainty principle says an uncertainty in the position is related to an uncertainty in the momentum. So already you can sort of imagine that the momentum and position are, in some interesting way, hooked together. Noether's theorem has really provided that hook in the rigorous way. Wow. There are other symmetries of nature where the Noether's theorem applies. For example, I do my experiments today and then I come back tomorrow and I do them, and I already did that yesterday, and the laws of physics aren't changing. There is a symmetry. The symmetry is a time translation. At different times, that's a different perspective. The laws of physics are the same. So what is a corresponding symmetry? Corresponding conservation law? Noether's theorem tells us an answer. You work through the mathematics. The conservation law associated with time translation symmetry is conservation of energy. Wow! So you can check conservation of energy in the laboratory, or you can verify that the laws of physics are not changing with time. They are coupled together. And once again, if you look at the Andromeda galaxy, think about that for a second. The light that was emitted from those stars was emitted millions of years ago, traveling through space all the time, and now we see it. So, not only are the laws of physics the same far away, they were also the same long ago. So this is a very, very powerful argument, and we've seen now out to billions of light years, and the laws of physics appear to be completely unchanged, even from then to now. This is a powerful confirmation of this law of conservation of energy. So it's not just a physics experiment that makes us believe that it's also this mathematical theorem. And I think this is why the US Patent Office refuses to consider the patents where you plug. Well, you don't plug something in and energy comes out. A perpetual motion machine has been dismissed by the US Patent Office as clearly unscientific. It violates the principle of the conservation of energy, and you might say, well, but what if somebody is really clever? Can't you get around the conservation of energy? And my answer is, well, I don't think so. Because A, we've tested it directly, and B, we know that the laws of physics aren't changing with time. If you build such a machine, then it also means that the laws of physics are changing with time. So maybe your machine isn't going to work tomorrow, and I'm certainly not going to buy it. So this is a Noether's theorem. Mathematics. Albert Einstein loved this idea. He was very impressed with Amy Noether's theorem, and it became a part of his general theory of relativity, where he was looking at deep symmetries of space-time. And this theorem allowed him to connect these to very powerful conservation laws, which are useful in the mathematical statement and application of the relativity. I want to tell you about one more symmetry of nature, which is very abstract, and it's going to hook in with Noether's theorem, but it also has a sort of a story to tell all of its own. This is the toughest part of this lecture, for sure. So if you don't get it, just roll with it, okay? Try to observe what you can, because I can't describe the symmetry to you in sort of obvious terms. This is very abstract symmetry of nature. It's got that name, gauge symmetry. Gauge symmetry. Yes, gauge symmetry. And even the name, it's some historical name, has something to do with railroad track and the gauge of the railroad tracks. But I don't have any idea why that word is associated with this symmetry. Oh. Gauge symmetry. Let me try to give an example that kind of hints at what gauge symmetry is. It arose in the theory of electricity and magnetism. In the 1800s, people observed that the laws of electricity and magnetism were symmetrical. They were invariant under a certain change. So let's think of the simple electric circuit. You've got a car battery and some wires going to a bulb, like the front light bulb of your car. And you hook it up and the light bulb glows. The laws of electricity and magnetism allow you to make predictions. How bright will the bulb be? How long will it burn? How hot do the wire get? And so on. These are consequences of the laws of electricity and magnetism. Now, when you have a battery, one side at 0 volts and one side at 12 volts, and you need to know that in order to do calculations. So physicist A does their calculations saying this side of the battery, the left side, is at 0 volt, and the side of the battery, the light side of is at 12 volts. Now physicist B comes along and says, they don't know what physicist A has done. Physicist B says, the left side of the battery is at 12 volts and the right side of the battery is at 24 volts. Okay, the difference is still 12, but they have picked different numbers. And now here is a big question. Does the physicist B comes to the same conclusion about the observable, the light bulb and the wires? And the answer is yes. It's completely irrelevant what numerical values you assign to the left pole and the right pole. All that matter is a difference. So the number doesn't matter. That's a symmetry of nature. You can pick this point to be 0 or a different point to be 0. That doesn't matter. You can change that and the end result are the same. Wow. So, as I said, it's a rather abstract symmetry of nature. That's the essence of gauge symmetry. Gauge symmetry is a little bit deeper gravity. Wow, I'm sorry, a little bit deeper than that, but that's the idea. You could also think about the analogs with gravity. Okay, I put an object like my fist at the top of the table, and I say, how high is that fist? Well, I could say it's zero above the table. Or I could say it's 2 feet high, it's 2 feet above the ground. Or I could say it's 150 feet above the sea level. It really doesn't matter what number I associated with how high this object is. Because in the world of physics, what matters is always changes in height. As I lifted it up, how much work did I have to do? I either go from 0 to 1, or I go from 3 to 4, or I go from 150 to 151. Or whatever numbers I'm using, it really doesn't matter. That's kind of like a gauge symmetry. It's a symmetry of nature. So Noether's theorems says there must be an associated conservation law, and as usual, you'll never guess it. You got to work through the math, and the conservation law that springs out of the mathematics is quite spectacular. Gauge symmetry in electricity corresponds, according to the theorem, with the conservation of the electric charge. So that's one of those eye-opening surprises in a junior level physics class when you first teach Noether's theorem. That makes people kind of get excited about this theorem, because conservation of electricity charge is so powerful and so useful in a wide variety of experiments, not just practical physics. and it comes from this abstract mathematical symmetry of the starting theory that doesn't really seem to have necessarily anything to do with counting up charges. Gauge symmetry goes much beyond Noether's theorem, however, and that's where I want to finish up today's lecture. We constructed our theory, we, Feynman and Schwinger, and Tomonaga, and the various other people like Dyson, who are many people involved in the discovery and elaboration of the quantum electrodynamics. Remember what they are doing. They are trying to come up with a quantum mechanical theory that takes all of the 19th century understanding of the electricity and magnetism, including the concept of the fields and electric charge, and make it consistent with the quantum mechanics. So, when they tried to do that, they already knew that gauge symmetry was a good symmetry of electricity and magnetism. They knew that whatever quantum theory they were going to write down, it must obey the law of gauge symmetry. That is to say, it must be symmetrical. Whether you call this point 0 volts or 10 volts doesn't matter, only differences matter, right? That's got together built into their theory. So, as they are constructing the theory of quantum electrodynamics, they have to be very careful. They are modifying it to be consistent with the quantum mechanics. They have to be careful not to modify it in such a way that you lose gauge symmetry. And what they discovered, this is very difficult to grasp the first time through, is that in order to make sure that the quantum theory is going to be gauge symmetric, they have to introduce a new particle of nature, the photon. Yes, it's not that you stick it in the theory because you know there. You have to put it in order to preserve the gauge symmetry. It comes out from the principle of the gauge invariance. That's a fancy word for gauge symmetry. So, think about it. Not only does the existence of the photon come out, but its properties. It has no mass, it has no charge, but it does have a spin. The photon has a spin 1. It's a boson. All of those facts about the photons are coming out simply from the requirement that the theory be gauge symmetric. Think of the power here. Once you have a symmetry that you believe is present in nature, you are starting to predict not only the existence of the particles, but also their properties. And so, in the later years, when people began thinking about the strong force between the quarks, the color force in the quantum chromodynamics, people are struggling at first to construct a theory. They don't have electricity and magnetism, classical electricity and magnetism to work from. Now, you've got the harder job of creating the whole theory from scratch, and gauge symmetry is a guiding principle now. You say, gosh, gauge symmetry was true for the electricity and magnetism. What if it's true for the color force as well? It's an idea, and now you work out the consequences. If gauge symmetry is true for the color force as well, then there must be a particle of nature that carries a strong force. We now call it the gluon. Yes, gluon. It must have certain properties. It has no mass. It has a spin 1. It carries color. All that comes out of this theory. So, not only the existence, but also the properties of the gluon are forced upon you. Wow, 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 wow. So, when people discovered this, it was matching with the theory and the data. People got really excited and they said, hey, gauge invariance is a great thing. So then, later, when they started trying to understand the weak force of nature, which was even more complicated and even more esoteric and even more bizarre, people complicated and people said, well, what if gauge symmetry is a principle of nature? and this time around, they predicted the existence of the particle, the center of the weak force, not the W, but the Z particle. Wow, Z particle, which nobody had ever seen, nobody had ever thought of. It was just because of the principle of the symmetry that they were able to predict the existence of the new particle, and the new particle means a new forces of nature, new force of nature. It was a new aspect of the weak interaction that nobody had ever thought about before. And it was real. It was there. They went out in the laboratory, took about 10 years, and they found it. So I think at this point, symmetry as a general principle is deeply required and deeply admired. It's useful, it's powerful, it's a part of the way that physicists look at the world. As we reach out and try to understand new physics, physics beyond the standard model of the particle physics, because we are still working on our understanding of the world, symmetry is still, and probably always will be, now a guiding principle. You look for the symmetries, and when you find them, you use them as a tool to understand the world. Thank you!